guys, so I'll just do a couple of the questions from the last worksheet. Okay, so starting with 8. Electric field strength. So you have the formula F equals QE, yes? So E equals F over Q. So you can say electric field strength is the force felt per unit charge in an electric field. That would be fine. Calculate the electric field strength at a distance 24 centimeters for a point charge. So you have to use the formula F equals K Q over R squared. Yeah. What did I say the K was? 1012, okay. And the charge is 65, 10 minus 9, all over 24 centimeters squared. Okay. What does that come in as? Do you have, come on, calculator, please. Where is everybody today? Yes, but why? 116. 116? 10 to the 6. Okay, and then part C is what's the force? So force equals QE. Yeah. So 1.6 times 10 to the 6 times 65 times 10 to the minus 9. So what's that? .0 newtons. Yeah. Yep. Okay. 9. A is the same. B. So you have this diagram here. Can you see it? The oil is between two plates, and there's an electric field. It has an equilibrium. What is the value of the electric field? Okay, so if we look at it here, there's an mg going down, and then there's a QE going up. So if it's balanced, we need QE to equal mg. So then E must equal mg over q, which is 3.06 times 10 to the minus 14 times 9.81 all over, oh, we don't have the q, do we? Oh, but we don't need, yeah, sorry, we don't, we don't actually need to use this formula because we have the V and the D, don't we?
Yeah.
So we can just say E equals V over D, which is 1500 over 0.02. What's that, so?
75,000.
75 kilo newtons per coulomb. Okay, so that's the A part. Well, the B part is they want the charge, basically. So we have QE equals mg. So Q equals mg over E. So Q equals 3.06 times 10 to the minus 14 times 9.81 all over 75,000. So what's the charge here? Thank you. Coulombs. Now, you know from chemistry that something will have a charge if it has more or less electrons to cancel the protons. Yeah? So in this example here, they tell you that this is a negative charge because it has an excess of electrons. What's the charge on of one electron? Yeah, it's minus 1.6, is it? Yeah. Times 10 to the minus minus 19. So one electron has this much charge, and your oil has this much charge. So if we just divide the two, we can get... Hey, why are you late? Why are you late? Ah, no, you're too late. No. You know how much it annoys me when people are late for physics because they go to SPAR. Go. Yeah, so go. Okay, can you type this in? 25?
Yeah.
Okay.
Just the constant for each electron will be given in exam,
yep.
or is something you should...
No, it's in the formula book. Okay. Part C. Draw the diagram of electric fields around an electron. Okay, so there's your electron, and the electric field goes like this. It's strong here and then weaker when you go out. Strong, weaker, strong, weaker. You get the idea. Strong, weaker. Ah, look, it's terrible. You get the idea. Okay. What is the value of the electric field strength at a distance 10 to the minus 8 from the electron? So that's E equals KQ over D squared, 1.4, 10 to the 12, 1.6, 10 to the minus 19, all over 10 to the minus 8 squared. Okay, so what's that, please? What is it? 2.25? 2.24? 10 to the 9 newtons per coulomb. Okay. Yep. It's not that difficult, is it? Let's have a look at 10 now. Can I scroll down? So in 10, you've got an electron around a proton. So there's your proton. There's your electron. And the radius is 0.05 nanometer. What's the force between them? K Q1 Q2 over distance squared, 1.4, 10 to the 12, 1.6, 10 to the minus 19, and it's another 1.6 and another 10 to the minus 19. One for the electron, one for the proton. All over 0.05 times 10 to the minus 9 squared. Okay, so just type that in, please. Tell me what you get. Okay, thank you. So that's the A. The B is they want the speed here of the electron. So we have to use our circular motion formulas. We have m equals mv squared over r, yeah? And we know what the f is, and we know what the m is. So yeah, this is fine. So v equals F over m with a square root. So v equals square root 0.05 times 10 to the minus 9 times 14.34 times 10 to the minus 6 all over. And what's the mass of an electron? You have it on your calculators. Are you giving me the final answer? Or the mass, the electron? I need the mass of an electron. Don't leave me hanging. What is it? Like 1.67 times 10 to the minus 34?
7.17 times 10 to the power minus 60.
For what? Look, just tell me what the mass of an electron is, please. Don't make me look it up. Hold on. Is this the mass of an electron? Is it? What is this? Go ahead.
9.11 times 10 to the 12 minus 31.
Thank you. Okay. Now give me the final answer. Thank you. Thank you. Alright, see now, draw the electric field lines. So, here's my proton, here's my electron. I'm not sorry, draw that a bit better. This is what it looks like here. You go from positive to negative.
Doesn't matter positions of proton and electron.
What do you mean? In the diagram?
Yes.
I know, they just put them anywhere and draw it. Okay. D calculate the force of gravity between them. So that's Gmm over d squared. 6.67 times 10 to the minus 11 times the mass of electron, 9.11 times 10 to the minus 31. Now I just need the mass of a proton. What's the mass of a proton, please? 10 to the minus 9. Sorry, nano is minus 9, yeah. Squared. You're giving me mass of the proton? Minus 27, okay. 1.67 times 10 to the minus 27. Alright, so what does that equal? Come on, tell it in Spanish. It's very small, and it should be. Yeah. Okay. Now there's one other question which I didn't give you, which I'm going to do now. I'll draw it for you. So this will be number 11. I started doing something like this last time. You have 4 microcoulombs, 2 microcoulombs, 2 microcoulombs, and these are all inside of a circle. So my first question is, what is the electric field strength at the center due to the 4? So right here, I want to know what's the electric field strength due to the 4. So that is KQ over d squared, which is 1.4 times 10 to the 12 times 4 times 10 to the minus 6, and I tell you the distance is to the radius 4.33 times 10 to the minus 2 meters. So 4.33 times 10 to the minus 2 squared. What's that, please? Thank you. Now, the next part of the question is, what is the electric field strength provided by all 3? Okay, now please look, so this is a little bit new, so look up. Electric fields are also vectors. So this here 2.987, look up, this 2.987 newtons per coulomb, that's actually directed this way towards the 4. Okay? Now these 2 are going this way, and I can calculate the strength from these 2 doing the same formula, but you realise, the only difference is this is a 2 instead of a 4, yes? So in fact these will just be half of this number. So can you tell me what half of that number is? So we have 1 going up here, 2.987 times 10 to the 9, and then
1.493 times 10 to the
1.493 times 10 to the 9, and then there's one here, 1.493 times 10 to the 9. And electric fields they're just like forces that you can add and subtract them, because if you think about it, you have this formula, F equals QE. So electric fields add together like forces. Like for example, e.g., if Q equals 1 coulomb, okay, then you have F equals E. So you can add electric fields together the same way you added forces together from semester 1. So what we can do is we can break this up into a piece this way, and a piece this way, and a piece this way, and a piece to the left. You'll notice that this will cancel this. And so what you're left with is 2.987 times 10 to the 9 minus, these two are the same, 2, and we just need this angle here. Does anyone know this angle? If they're all the same distance apart, each of these angles is 120. So this one here is 60. So this one here is the cos of the sine. Cos. So it's 2 times 493 times 10 to the 9 cos 60. Now if this is positive, it's going up, and if it's negative, it's going down. So can you type it in and tell me what you get? It should be negative. I think this is negative. 9.59. Something, maybe? No, not 9.9. But tell me what you get.
$1.494 times 10 power 9.
1.494. Yeah.
Times 10 power 9.
And was it positive or negative?
Positive.
Ah, so it's going up then. Yeah. This question came up last year and the year before last. So this question came up twice in section A in the last 2 years, and most students didn't do it. In fact, all students didn't do it. I don't know why. Is there any questions that you have about this? Questions? It makes sense? Yes? Yeah? Okay. Alright, I just need to double check a picture of something before I start telling you what it is. I'll check it later. Okay, we'll go on to the next topic now. Yeah. So far we've done 2 types of fields. What are the 2 types we've done? Gravity is the first one, and what was the second? Electric. So there's one more type of field which we need to look at. Well, do you know what it is? So we've done gravity, electric, magnetic, yeah. So, north, south, well that's bad, but you get the idea. So, our last type of, yes, it is north, sorry, north-south. Our last type of field is magnetic fields. What do you need to know about magnetic fields? Well, number one, they always are in north-south pairs. Always. So what I mean by that is, where there's a north, there's also a south. You can't have just a north or a south. You have to have both. They're always in pairs. And just like electric, the field can vary due to material or / space it is in. So do you remember what was one way we could block an electric field? Yeah, some plastic or something. Is it possible to block a gravitational field? No. But a magnetic field you can interfere with. You can block it as well. Anyways, sorry, do you have that? Yeah. Does anyone know for gravitational field we have gravitational field strength? What letter was that? That was G, and that was newtons per kilogram. And then for electric field that was E, and that was newtons per coulomb. Does anyone know what it is for a magnetic field? How we measure its strength? Does anyone know? No. So we have magnetic flux is what we call it, and this is the symbol for it. And the unit, does anyone know the unit? Almost, Tesla is the next thing. Weber, WB. Now, this number here magnetic flux Earth. I just want to give as an example the one for Earth, just so you can have an idea of how big this is. So, as you know, for Earth acts like it has a big magnet inside of it. You know this. So you have your magnetic field going around like this. Does anyone know what's inside the Earth that makes it have this magnetic field? Do we know? I think it's melted iron, liquid iron. Liquid iron is what is acting like the magnet here. Anyways, let me just see if I got my number here. For Earth, so there's the picture there nicely. Come on, how strong are you? Oh, I can't find it. But if I remember it correctly, it's quite small. It's something like 0.0 1 Weber, I think. So I just wanted to give you a number so you can feel how big these are. And what do you think is the strongest magnet that's been made? Would you know? The strongest one is, I read it last night, it's only something like 17 Webers, okay? So the numbers here aren't too big. I just need to get my picture back. Yeah, we go. Okay. So anyway, that is magnetic strength, magnetic flux, and often we don't care about that. Often we care about this. Here is your magnet going from north to south, and often we care about how much of a magnetic field we have per area. Okay? This is called, I think now, Ira, you have the correct unit. Do you know what this is called? That's the unit, yeah, but what is that called? Magnetic flux density. Written by B. And the formula is, it's magnetic flux per unit area. And the unit here is the Tesla. And 1 Tesla equals 1 Weber per 1 meter squared. Okay, so for magnetic flux, we only care really about how much we have per unit area. Okay? Now, if I have a north and a north, do they attract or repel? They repel. And if I have a north and a south, they attract. If I have a north and a south, and I put an electron in between, does anyone know what would happen to the electron? Nothing would happen, right? Why not?
Because it has not been moved. I mean, it doesn't cross the
Is there... What do we think?
It doesn't cut the magnetic.
It does. It's in the middle of the magnetic field. Huh? It does nothing. Okay? So this is where we have to be careful. That's an electron, it has a charge. That's a magnet, it has a magnetic field. The electron doesn't move. However, if that electron is moving, yes, then it will feel the magnetic field. Okay? So this is our important note. A stationary charge will not interact with a magnetic field. But here's the big however. However, a moving charge will. So I find this quite remarkable, really, that if the charge is not moving, it doesn't feel the magnetic field. However, if the charge is moving, then it does feel a force. So if you have your electron and it's moving with velocity v, and it's in a magnetic field B, and remember B is Tesla is the unit, okay? Then the force is equal to, this is the charge, QVB. But there's an important condition here. Now look, you get my picture here. Okay, so current field is the first one. Okay, so this is, you might remember this from high school. There's that star there is me telling you that the force goes in a very special direction, and you can find it by using your left hand. Okay, so first finger here is the direction of the field. Okay, and then the second finger here is the direction of the current. So then this one here is the direction of the force. So notice how the force is perpendicular to the current and to the field. Sorry, this is the field. This is the current. I'll get the picture back up. Let me show you that in an example. Yeah, field is first. Current is second. So for example, suppose we have a current going this way. Which way are the electrons going if the current's going to the right? Are the electrons going to the right? No. Huh? Opposite. The electrons are moving to the left. This is in electricity, it's the rest are one. Now, if I put a magnet here, north, south, so there's a magnet going this way, which way will the force be on the electrons? Okay, so what we do,
Not the stuff.
first finger, north to south, so that's going up. And which way is the current going? Left or right? The current's going to the right, because the electrons are going to the left. So then which way is the force? The force is to you. Okay? So what will happen to these electrons? As the electrons move to the left, will they move out of the screen or into the screen?
Oh.
They'll move out. Yep. So the electrons want to move out. Okay. So you have two formulas. This first formula is when you have one charge. But what about if you have a current? You have many coulombs per second. Well, it's very, very easy to get that formula because do you remember what I is equal to? Q over T. So then what does Q equal? Q equals IT. Yes? So if you want, you could just put that in there. So you get F equals ITVB. But yeah, I'm getting to it there. But also, if you look back here, let's say that this here has length L, and the velocity here is V. You know that V equals L over T for each of these electrons, yeah? So what you can do is you can replace this V with L over T. And they cancel, and you get this formula. F equals B-I-L. So you have this one, or this one. F equals Q-V-B.
Could you show L over T?
In the picture? It's just the length of the wire divided by the time. That's the velocity of the charge. So we use this one when we have a single charge, and we use this one when we have a current flowing. So these are the two formulas for charge in a magnetic field. And both of these, use the left hand rule. Okay. I want to do another formula with you. Can I go down? Yeah. So let's say we have our charge moving this way, and let's say we have our magnetic field going this way. So which way is the force? What's this first finger for? Field, so that's going up. And then, is the current going left or right?
Right.
Well, I didn't say what the Q is. If I say that the Q is positive, then it's going to the right. So which way is the force? The force is going towards you. Okay? So can you just picture for a moment, what I'm going to do is, I'm going to look at this from the top. So then which way does the the proton, which way will it go? It will swing out this way, okay? I'm looking at it now from the top. So if I draw that from the top, the electron comes along and then it turns in a circle when it enters the magnetic field. Yes.
So the hand rule for the one
just this?
Yeah.
Which, well, okay.
The one and zero.
This one.
Yeah.
The field is going
Up.
up, and the current is going to the right. So then the force is going to you.
So if Q is more than zero, it means the charge is going to the left.
If Q is less than zero,
Then
it's an electron. And we say the current is always the opposite flow of the electrons. So if an electron goes from here to here, then we say the current is from here to here. But if a proton goes from here to here, then the current, yes, is from here to here.
Yeah, but I'm confused with the charge. Like if it's more than zero, then should it go to the left or right?
Q is more than zero. I'm just saying it's a proton going to the right.
Oh.
Yeah. If it was less than zero, it's an electron going to the right,
Yeah.
so then the current is going to the left. Like, let's continue?
Yeah.
Yeah. So here, what's the force formula? It's Q, V, B. But what type of motion is this? What type of motion is this? What type? circular motion. Because what will happen is the electron will come in, and then when it enters the field, it gets pushed around. Okay? So there's another formula for force circular. You can have F equals mv squared over r. Yeah? If I put these together, I get mv squared over r equals qvb. So that cancels that. And I get r equals mv over qb. Now, why is that formula useful? Well, the reason it's useful, it's the same reason it's useful because of your mass spectrometer in chemistry. Yeah? How does your mass spectrometer work? You take your substance and then you heat it up, isn't it? And then you give it a charge, electron go and fires at it, so then it has a negative charge.
Yes. It stays
Does it free the electrons or does it attach electrons? It frees electrons, so then it has a positive charge, is it? Yeah. Okay, and then what happens? It gets
the
magnetic field, and then
it gets attracted according to mass charge ratio.
which is exactly this here. You see, the radius depends on the mass per charge, because the velocity and the magnetic field density, they are a function of the machine. You know, you could have the B whatever you want, and you could change the B. But the mass you can't change, and the charge you can't change. But what happens if you have more mass per charge? Does the radius get bigger or smaller? It gets bigger. And if you have less mass per charge, it gets smaller. So what happens is, when this goes through the magnetic field, it spins off in a circle, but the radius of the circle depends on the charge per, the mass per charge. So you were learning in chemistry that the mass spectrometer separates it by mass per charge. And this is the reason why. Because you have here, radius is proportional to mass per charge. But remember, this needs a V. What if the charge just sits here? Will it move? No, it needs a V. So often what we do in the mass spectrometer, can I scroll down? You have something like this. You have a plate with a hole in it, and then another plate with a hole in it. And then here's a big battery. So you get an electric field here. Yes? And then what happens when your Q enters the electric field? What's the formula for the force? Force equals QE. So this gets a force. But force is MA. So in other words, it gets an A. QE over M. So when it reaches the hole at the end, is it going faster? Yes. So then it exits the hole, and then it enters a magnetic field, north-south. Now you said this has a positive charge, is it, in your mass spectrometer? So the field is north-south, So in this, the way I drew it here, what would happen is, when it enters this field, it will be deflected up. And we've seen that this radius here is equal to m over q times, what was it? V over b. The b just depends on the magnet. And the v, well, the v you can control by changing this here, because you have the formula v equals u plus at. But what's u? U is 0, so you have v equals at. Or, if you think about it like this, v squared equals u squared plus 2as. The u is 0, so you can get v equals square root 2as. Now the a, you have it here, and the s is this distance here. So if you want to make the v bigger or smaller, what could you change? Well, you could change the a or the s. And if you wanted to change the a, what would you have to make bigger or smaller? Well, you can't change the q, because that's the particle. And can you change the m? No. What about the e? Yeah, what's the formula for e here, for these two plates? It's the voltage divided by the distance. So, if you look here, you can have v equals root 2qe over m times s. v equals root 2q over m, v over s times s. So you get the velocity equals square root 2q over m times the voltage. So if you want to change the velocity that the charged particle enters the magnetic field at, you can just change the voltage of the battery.
Above that velocity.
Yeah, sorry. No, which v? Inside the square root? Outside?
The radius.
Yeah, sorry. This one here, this is velocity, this one here is voltage, and that one up there is velocity.
Oh, velocity.
Yeah.
So in question, will the velocity be given? For the, in case if we were to find the radius, will the velocity be given?
Oh yeah, well, I'll look at an example here, but let's see. You know what? Actually, I haven't seen it in the exam yet, when I think about it. It's in the formula book, but it's not. It hasn't been an exam question yet.
The formula?
Yeah, for the OR. So I don't know how they would do it in the exam, because they haven't done it yet. I would imagine though, if this came up in the exam, they would break this question up into a few parts. Can you look? If this was an exam question, what they would do is, they'd give you the voltage and the distance, and then what do you think they would ask you for? The E. Okay? And then in part 2, they give you the Q, and then what would they ask you for? The S. And then in part 3, they'd give you the mass, so you can use F equals ma to get the A. Then in part 4, they would say it starts at rest, and you know what the distance is, so what could they ask you for? They could ask you for velocity, yeah. Then, the second part of the question, it could be it enters a magnetic field. So then part 5 could be, what's the force in the magnetic field? And then part 6 might be what's the radius then, of the circle. Something like this. Now, I'm just imagining this because they haven't asked it in the exam. But I'm imagining if they were to ask it, they might like to do it in 2 parts, like this. An electric field, then a magnetic field. Okay. Finally, can I scroll down? You have your formula F equals QVB and F equals BIL. But if things aren't perpendicular, then we need this sine theta in it. So for example, here, if here is the I, and here is the magnetic field, which way is the force going? Towards you. Yeah? Now, this only works if this is at, where's my pen gone? 90 degrees. Okay? If I change this a little bit, to theta, the force is still towards you. Okay, the force is still towards you, but it's not as big. You have to multiply it by sine theta. Okay? But it's still towards you. Okay? It's just not as big. You multiply by sine
So
theta.
in other words, use the formula beside 90 degrees. Any angle beside 90 degrees.
Which formula?
The sine theta.
Oh yes, any time that they're not perfectly perpendicular. Yeah. In fact, Thomas, you can still use it when it is perpendicular because what's sine 90? It's 1. So in fact, the formula with the sine theta works always. Oh, jeepers, didn't realise it's that late.